Hello and greetings from IIT Kanpur. We have been looking at unit processes for VLSI fabrication as well as semiconductor processing. So today we will be looking at a little wider aspect of unit processing, an area which is called thin film processing. So let's get started. So we look at thin film processing, make the pointer on. This is the disclaimer. So this will be the outline of what we will be discussing in this lecture. First, I will be introducing what are thin films. It's actually in English, of course, thin films. It's obvious, and of course, the meaning is the in technical meaning is similar to that, but it specifies something. Let's see what it means. We'll talk about thin film growth, how the growth take place for a thin film, and the whole process. A little bit of the detail of it. Next, we look at the structure that we actually end up finding in thin films. What are the aspects which are something which you should watch out for? Of course, it varies according to what you are wanting to do, what type of thin film you are growing. Then we will talk about the mechanical properties that you usually are concerned about in thin films, and the electrical properties that you are concerned about in thin films. So for this particular lecture, I would recommend Wolf and Tauber as a reference, especially chapter 4, very comprehensive and nice method way in years presented. And this is the other textbook, which of course we have seen this in an earlier context also. This is a book on electronic thin film science for electrical engineers and material scientists. So this is a full book. So there are lots of information in that for somebody who wants to dwell deeper. Okay, and this has been authored by 3 authors, Tu, Mayer, and Feldman. And whenever I have taken some materials from these, I have tried to give references. But independent of that, those who want to specialize should look into read up these references. So first, when we say thin films, where does it occur in VLSI? Do we need to look at in VLSI? Is it only in some specialized thing, or is it much more pervasive? And the answer is it is quite pervasive if you look at in the VLSI fabrication. This is the schematic diagram which we have come across when we discussed process integration. And if you look at it, there are various levels and various structures here. A lot of them actually can be classified under thin film processing. We have the metals, where you deposit the metal layers. Then you have the oxides, the BPSG in this case, they are all thin films. You have the nitrides. Of course, I am not showing all of it. There are lots of varieties you may find in an actual VLSI chip. Silicon nitride. Then the silicide that you make. Okay, the silicide that you find on top of the poly, for example, and similarly on top of the source and drain, which I have not indicated the arrow to avoid it from becoming cluttered. Then you have the polysilicon. The polysilicon is which helps form the gate. The deposition process of that is a thin film process. And then you have the gate oxide growth. It's actually a special type of thin film where you actually use the material from inside, similar to silicides, where the substrate itself is used. And then you have many others in this, which will be maybe specialized process, maybe some. For example, today hafnium oxide is being deposited, right? That would be a thin film process, and so on. So there are many other aspects which actually fall under the broad category of thin film processing. Now, this thin film processing is a very generic term. If you look at it, there are so many varieties of thin films that you end up forming. There is no one single idea that describes everything. But there are some things which are common to all, which is what we will try to discuss in this particular lecture. So thin films may be of the thickness of nanometers all the way to hundreds of micron. Okay, it can be really a wide range. So you are talking of several orders of magnitude thicknesses, and clearly the whole process, the properties, all that will vary according to the thickness and the material that we are using. But the key point about thin films is that when you are forming these films, the lateral dimensions are much larger than the thickness. Or put another way, the thickness of the films is much smaller than the lateral dimensions. So, the thickness in the vertical direction, if I may say you hold a wafer and we are looking at it, typically vertical dimension, they are very small compared to the lateral dimension, and the way you form those films is what we are going to be looking at, and what we have to watch out for in this. Of course, we will be looking at in greater detail at some of the thin film processes in the subsequent lectures, but this is to capture the overall commonality so that we do not keep repeating stuff. Typically, in thin films, the key part about thin films is the surface properties often ends up dominating than the bulk properties. The bulk effect, because the surface area is much more than the surface area to volume is much larger compared to many of the bulk materials that we encounter, and that brings in special aspects. In fact, you can play around with the properties, and that is where the advantage comes of using thin films. So, let us see what would be the thin film requirements. As I mentioned, thin films would have a high surface to volume ratio. So, that means the properties are likely to be different from the bulk material. But what is of particular importance to us is these properties that you have, they can be tuned, they can be controlled by the structure of the film that we end up forming and the method by which we form. We could have a very rapid deposition, we could have a very slow deposition, we could have a higher temperature during deposition, lower temperature during deposition. By tuning this, essentially we are getting a wide range of properties at our disposal, and what we want for our VLSI we will use according to the requirement. So, typically what are the properties or what are the requirements of these that we need to watch out for? There is no, I am not prescribing what should be done, but what are the properties that we want to watch out for, and according to the need you will choose it. First is, of course, the thickness should be controllable. Remember that when you are making something which is a few nanometers, you better have much better thickness control. So, the way in which you will be depositing will be different than when you want to deposit say hundreds of micron. There a few nanometers here and there might not affect the, it should not typically affect the overall final properties. So, thickness should be well controllable in these thin film processes. After the films are deposited, as we have seen in the whole VLSI game, planar process, we end up etching away what we do not want. So, that means typically these thin films we want them to be etchable. This is something that you desire. So, what you do is you have to make sure you choose things which can be etched. Sometimes if a good etchant is not available, in spite of all the good properties of thin films, they take a long time to come for actual practical implementation. So, but then of course you can get around those things. Copper is a great example. Copper etchant was not available, and that is one reason copper could not be used for a very long time. But then they had a workaround on that, and as we saw earlier, we could use the Damascene process. But at least you should be aware. But if you can etch it, it opens up a lot more avenues for you for processing of the using it in the processing and incorporating in the device. This is one of the biggest challenges in terms of the practical implementation. When you are forming these films, and especially the requirement for VLSI, where a few defects can make a big difference in whether the whole chip survives or not, right? So, you want to make sure that the films that you are forming, you can be with a very high probability certain that there are no defects. Low defects, and typically these defects often manifest themselves as pinholes. That is, if you are forming a film, there is a small region where the film has not formed or it is very thin. That means that is a weak spot, could be a weak spot. And for example, if I make an oxide and I am using it as a dielectric, so if there is a weak spot, that is where probably the first breakdown of that dielectric is likely to happen. So, you have to watch out for this. This also is a practical aspect. You need to make sure that what you are depositing adheres to the layer underneath, otherwise it may just come off, and that will be a failure point. Stability and reliability is one of the main aspects people have to worry about if they want to make a device which will sell in the market. So, it is not just when it is depositing, but actually even after depositing or when subsequent films are formed on top of it, it does not just come off. That you should watch out. So, good addition, and it should be under low stress. Well, when I say this, I am not prescribing low stress. There are situations where we purposely make it stressed so as to bring out some properties on the films underneath and so on. So, but by default you want things to be in low stress. Why? If something is in stress, it is wanting to move away from its position. If it is wanting to move away from the position, first option that it gets, there is a temperature spike. It will just do something to release its stress. That means it may end up messing up the device. Reliability will go off. So, but typically low stress is the default option. There are situations where you purposely make high stress and work around. Then you can have, then you need to make sure, and this is increasingly so, especially with the very high resolutions that are needing high packing density and high resolutions in lithography, you want conformal step coverage. So, any steps that are there, you want to be able to do conformally, and if you can do it conformally, remember the spacer discussion we had, you can achieve such you are able to achieve such structures. Okay, so that's why you may need that. And also sometimes you want to planarize the whole thing, right? So, it will help you planarize wherever possible. So, clearly these are some of the requirements of a thin film. Now, when you are using a thin film as a dielectric, you want to make sure that it has low K or high K. Each of them will have a different requirement. So, nowadays high K is becoming very important, especially for ultra small gate length transistors, because you want to be able to control the channel much better. So, high K is needed. So, high dielectric constant is needed. So, in those cases you will have to design it that way, design your film process that way, and similarly low K also you have to design. Low K, sometimes one of the low Ks that can be done is to make it very fluffy, which there's a lot of air pockets in them, and that way the K dielectric constant tends towards 1, right? Of course, reliability issues and all one has to work out, but there was actually a silicon low K dielectric which was tried. Okay, so there are cases where you can play around with these. So, you can the thin film requirements is you want the required dielectric constant. Similarly, conductivity. So, so we saw what the thin film requirements can be in the VLSI. But before we go deeper and look into various aspects of how the films are formed and what are its properties, we look at them a little bit more closely. Let's classify this thin film based on certain parameters, especially that of processing, because this is a processing course. Let's classify it based on that. So, what is thin film processing essentially about? It's about vapor phase material, that is materials available in vapor phase. It either reacts or comes to substrates and reacts, but finally that material that is coming in as vapor gets deposited on a substrate. It may react, it may form some other things, that's fine, but that's the main direction of action, if I may say so. So, vapor phase material deposited on the substrate primarily will help the formation of the thin films, and that's what we would call as thin film processes. This can be classified into two parts broadly. One case where the material that is coming in, it doesn't just get deposited on the substrate, and it doesn't just cling to the substrate. Maybe at the very small interface there will be some interaction, but it requires that the thing that is coming in will react with what is on the substrate and then transform that, and the interface will go inside the substrate itself. Okay. One example we have already seen is oxidation. Oxygen species comes in, it forms a, so it's coming and interacting first with the what is there on the surface, then goes in and interact with the silicon and forms silicon dioxide. Similarly, silicides also you will have the same thing. Nitridation also we have seen. So there are some class of material of reactions where the substrate itself takes part in forming of the thin films. Okay. Now the other case, it doesn't change the substrate. Doesn't mean that it doesn't interact. There may be a small monolayer, a few monolayers of chemical bonding is possible, but first order it doesn't change the substrate material. So this second category of that which doesn't change the substrate material, one can broadly classify into 3 different categories that you are likely to encounter in VLSI processing. One is using chemistry, chemical vapor deposition. Okay. So in this case, chemical reactions of vapor phase chemicals that contain the constituents of what forms the thin film comes in and gets deposited. This could eventually may be totally crystalline, molecular beam epitaxy. It comes in and falls on the surface, and then you design it such that the thin film that is forming allows time for the molecules to come and organize and form a crystalline material. But if you do it a little bit more fast, even before they can organize, they end up forming the film, right? Lot more material is there, so there's no question. Once everything is there, there's no question of rearrangement, right? It's difficult. There are situations where you could, but very often you cannot. So amorphous films can also be formed, and these are formed with oxides, nitrides, silicon, amorphous silicon, and so on. Please note that the examples I am giving are representative. The field is vast, constantly evolving, newer and newer ideas keep coming. So what I am telling is just a glimpse, but the broad categories, if you understand, you can also yourself classify the process and use it accordingly. You could also make it polycrystalline, and one of the popular things that you use is polycrystalline is of course silicon itself. Polysilicon is used. For example, the gate material is polysilicon, correct? This polysilicon has to be done in a different way compared to the amorphous. Amorphous is usually done with plasma enhanced chemical vapor deposition. LPCVD is what is used for polysilicon under certain conditions, okay? And that's something we will look at in the subsequent lectures, but at this point I want to say there is one category which is the chemical vapor deposition, where the chemical reaction, the vapor phase, they come and form this. Second, of course, chemistry, then you have physics, physical vapor deposition. Here you have dislodging of some target, and then you can you bring it outside and then make it deposit on the substrate, or you could evaporate something and make it deposit on the substrate. So these are some popular approaches for making physical vapor deposition method of thin films. There is another method which actually in the labs you may use more, and increasingly in some of the newer fields like say organic electronics or flexible electronics, you end up using some of these ideas, and you do use it in VLSI as well. Coating with a liquid which is a solution, and when the solution dries, you end up forming a thin film layer. This is used primarily in photolithography. In photolithography, there is the process of forming the photoresist, which we have seen. Briefly, we saw aspect of photolithography earlier. So when you form the photoresist, how do you do that? You have a solution of these polymers. There is a spinner. So you just put that liquid and then it spreads out. It's almost like making dosa, only thing that it's inverted. When you make dosa, you actually use a ladle to spread the batter, right? Here, the bottom disc spins, so the liquid just spreads out and forms a thin film, okay? So this is one thing that you may use for lithography. It's one place where you end up using. There are some other places also people try to use, for example, pre-deposition, they used to use spin coating method. We saw that when we discussed the pre-deposition examples. So people keep looking for innovative ways, and this can be one of the ways. Now we plunge into the key part of this process. We go into the thin film growth. and what can be called as condensation. Why is it condensation? We saw it is coming from a vapor phase. The constituent atoms primarily come from the vapor phase, and then they form the thin film. Thin film is a solid, so it's condensation. And let us see how this happens. If people have studied this very deeply, and we'll also go through it and try to get an understanding. It's common sense. Many of you might have observed it in your day-to-day life in various aspects. But when you're using it in VLSI, you better have a very thorough understanding of what happens, so that you can, as I said, use the properties according to what you need. And you change the process so that you get the properties that you desire. So, thin film growth. So, as discussed, we have vapor phase, which is initial, and this is time progressing left to right, at least for this and the next few slides. So, vapor phase, initial state, and then it finally forms a solid phase, condensation. But it does not just condense. There is an intermediate state we have to look at, which is where all the action is in terms of, primarily the action is in terms of how the thin film is going to get formed, especially if it is to remain thin. That is the intermediate phase, which we can call it as the add atoms. Okay, atoms that are adsorbed to the surface. So, we can look at this schematic. I have tried to show substrate, all these vapor phase species are coming. They are coming in random directions. They could be primarily coming in this direction because of some bias that could have been applied, we do not know, but it is all coming this way. And you find that there are a few which are on the surface of the substrate. This is what we will call as add atom. What causes this add atom? We should make sure that they come and form, deposit in the right way, so that the eventual growth should happen. Let us look at that closely. What causes them to come and stick to the surface? So, if you look at it, there is an interatomic potential which is there, and this has been well studied, and this is this is part of many aspects of physics and various engineering aspects. So, if you look at it, if this surface is where the atoms of the surface of the material substrate exist. So, if there is an atom that is there at a distance r, the potential that it will see due to this surface atoms as well as its own properties, it can be described by this form. This is a popular way in which you can describe it, phi of r, which is a potential as a distance of r. There are two components to it. One is a repulsive component. So, as the atom comes closer to the surface, when it comes very close to it, it comes close to the nucleus, and the nucleus of the original atom, they can repel, and there can be other aspects of it. For example, Pauli's exclusion principle will ensure that electrons cannot come in there. So, if with an electron cloud, if it is coming, it will repel it. So, what you find is the repulsion force increases as it comes closer to this, and in fact, far away it hardly sees the repulsion, but suddenly the repulsion force goes up at a very rapid rate. On the other hand, there is another force that is present when it is far away. There is some sort of attractive force that is trying to pull it, okay, and it keeps coming, and you find that it is becoming more and more attractive, but the rate at which the attraction increases is slower than the rate at which the repulsion increases. So, far away the attraction dominates, close to the surface repulsion dominates. So, this has been modeled in this form, and you can see 1 over r, the positive part is the repulsion, negative part is the attraction, and you have an optimum location at some A naught, which has a lower energy. If you look at the combined potential, which is the dotted line, there is a minima that is occurring at A naught. So, clearly all everything wants to be at the lowest potential, as you know. Gibbs free energy has to be lower. The overall energy of a system likes to be at the lower energy state, correct? So, if that is the case, the atom that the species that is coming will end up could get trapped in this minima, and that is the add atom. Okay. So, if you look at it, long range attraction, short range repulsion has been modeled, and there are many ways how to describe what is the form of this. This is a generic form which has been suggested, and in that the parameter P is 12 for repulsion and 6 for attraction. So, very close to the thing, it actually goes up very fast, very close to it, the other one tapers off, right. So, you find that the attraction is for Q equal to 6, and this could be one way to model what is known as the van der Waal attraction. Okay. Now, when it comes close, as I mentioned, Pauli's exclusion principle will prevent electrons from coming, right. So, electron cloud overlap is one of the first things that will repel, and so it will push it away. Those who have looked at nuclear engineering, you know that when you have a positive ion which is going to the nucleus, there also there is a repulsion, electrostatic repulsion that can start coming. So, there are various components to this, but broadly what we do as engineers is to get an understanding of what it is and make use of it. That is our task for technological purposes. So, here this is one of the standard ways in which it could be modeled. So, now let us again look at the continue looking at this a little bit closely. So, you have 3 diagrams, one below the other. So, this is the potential that you have, this is the force that the species that is coming from away towards the surface will experience, and below the A naught it will have repulsion, above A naught it will have attraction. So, that is where the minima, and it will end up settling there, and that is how the atom gets formed. Okay. Now, when it is coming from away from this side, there it has a velocity. We know momentum has to be conserved. So, when it comes there and hits the thing in the normal direction, the normal component of it has to be absorbed by the substrate. Usually that there will be some phonons or something that will end up conserving the momentum and the energy in that direction also. But remember, the lateral component need not be compensated. So, normal component is transferred effectively. The atom can have lateral velocity. So, when it is coming and sticking to the surface, if it is coming at an angle, the vertical component is what becomes absorbed by the substrate, but the lateral component is there, it is going back and forth. Of course, it could also be repelled by that in the vertical direction, they all happen, but it could get caught in the minima. Now, if the reaction to its normal component is such that, or during the course of it being an atom, there is a push from the surface side, the atom could also re-evaporate and it could go back into the vapor phase. Okay. Now, there is a broad classification of how this happens. The attachment of the electron, attachment of the atom without electronic transfer, that means that there is no chemical reaction. This is known as physisorption. But sometimes what happens is the nature of the atom that is coming from outside and that on the substrate, their electrons could interact when they are in that, when it is in that potential well, and they can form strong bonds. So, there the potential well will be deeper, and that would be termed as chemisorption. So, physisorption and chemisorptions are two classifications, and binding energies for physisorptions is tens of milli-electron volt to a few hundreds of milli-electron volts, 400 milli-electron volts and less, typically that is what people predict. On the other hand, chemical reactions, binding energies are much more, okay, several hundreds, more than 400 or 500 milli-electron volts to almost 10 electron volt, right. So, of the order of electron volts to 10 electron volt is what is chemisorption. So, this is something to be kept in mind. So, if you can choose something, if you want it to bind very well, you may go for chemisorption. Sometimes you do not want it to bind that well because you want some other subsequent reaction to take place or to move around the surface in order to arrange itself in a particular way, then you would prefer physisorption. So, now we have seen the details about the atom. So, now given some examples, there could be atoms that come together. So it is forming, and remember that is randomly coming, it could deposit anywhere on the substrate, but we saw that the lateral velocity is still there, so it keeps moving around. And that is similar to the diffusion situation that we talked about in the potential well, hopping from one location to the other. So as it is moving around, sometimes two add atoms and a few add atoms can come together and form some sort of a cluster, right? They starting to come together, and this coming together is what is known as a nuclei, and that's the start of nucleation. So one atom is there moving around, another is coming, and they come together, they formed, and then they now it says a new property. Okay, so there are two of the atoms together. Then this may be more favorable for another atom that is going around to join than join only a single add atom somewhere. Okay, so this is what is known as a nucleation. It will start growing, and this is the onset of condensation. So condensation has now started. This is where condensation actually starts. So let's proceed and see what happens when condensation happens. Before we see that, I just want to reiterate, some of these add atoms could also re-evaporate. It is fallen down, it's going around, doesn't find a nucleus, and suddenly some lattice vibration is pushing it out. Okay, so then it can come out. So that can also happen. So let's see what happens when the condensation has started, how it proceeds. So this is the first step which talked about nuclei being formed. So nucleation has started. So add atoms merge to form larger nuclei or may re-evaporate, as we saw. Some of them could be just there and then they can go back. And as they form, the nuclear size actually grows. Okay. Sometimes some of them will grow, some of them will shrink. That depends, maybe could depend on the size of the nuclei, depend on the temperature, depending on the condition. But typically larger nuclei are more stable, smaller nuclei are less stable. They could dissolve and give their add atoms to larger nuclei. That could also happen. So what ends up happening is higher sizes as they are formed, the nuclei starts to grow. Okay. Usually if there is a supersaturation of vapor phase, okay, supersaturation means a lot more atoms are available in the vapor phase and they are constantly bombarding. Sometimes nuclei size will not grow very large. Even before that, smaller nuclei are there and they start going to the next phase of this growth. But if it is very slow and rarely some atom is coming, usually I'll give it a time to grow and then the nucleation part is more visible. So theory clearly shows that the Gibbs-free theory has been validated by observation, and which Gibbs showed it in the case of water molecules coming together and how they coalesce. So Gibbs free energy reduces as these smaller nuclei become larger and larger. So what is happening is add atoms are forming all around this nuclei, but instead of forming a new nuclei, they come to this existing thing and the original nuclei starts to grow. As they grow, we have what is known as coalescence. So these things, as they keep growing, a few nuclei, large nuclei may submerge, and then they may come and form a larger particle that is there on the surface, right? So, and they coalesce in this form. Now, once they coalesce, the film growth starts, because it is not just the surface. It may even go to higher directions, upper dimensions. It's not just in the lateral direction, but higher dimensions. Of course, upper dimensions growth is little lower than the lateral dimension growth. So these nuclei, they come together, they coalesce and form larger entities. And sometimes the ones that are nearby, they also come in, but they go to the higher level. Okay, so it forms a three-dimensional structure. So you find island stage of growth is initiated with 3D growth, more on the parallel direction of course, but vertical also is present. The coalescence starts with larger rounded shapes forming well-defined crystallographic shapes. Initially you had them forming in blobs, usually circular or close to circular. But now they form some crystal orientation. It depends on the nature of the atoms that are present. They may show their crystallographic behavior. and as you can see, it is shown schematically here that they are having some hexagonal shapes, and then these shapes also merge, okay, and so the coalescence continues. And another thing happens is, in these empty spaces, as this coalescence takes place, nuclei there is no nucleation there. The nucleation that was already there, the nuclei are all pulled up. So new nuclei can get started in these empty spots also. That is called secondary nucleation. So as that continues, you will find that all these merge and you may end up forming channels and holes. These holes you have to be careful. If you go very fast, you may end up having what is known as pinholes, right? Some holes may exist. So you want to make sure that you control it such that these channels and holes will slowly get filled up. So as more and more deposition continues to happen, the height of these films of these in these areas where they are coalesced, they become more and more, and the empty spaces that open up, there you may have secondary nucleation and new nuclei will start forming and they will start to grow. If they end up coming closer contact with the larger coalesced body, they may end up getting merged also. So islands continue to form and they grow behind the channels and the holes. So you can see even in these newer nuclei and forming and coalescence are forming. But at this stage, the crystallographic nature will be more evident because it's going into a three-dimensional shape and it's slowly becoming thicker also, although the horizontal dimensions is much larger than the thicker dimension. So this is how it is formed, and now as it continues, eventually these channels will and the holes will get covered up. So you will have a continuous film. Okay. There are lots of factors that play a role here, what temperature you are keeping as a substrate, what rate you are growing, so all that has to be considered. And then eventually you will have a continuous film. Okay. So we have seen how the growth takes place. Some of us might have seen also how if during rainy season, how water in a glass pane, how they come up and they form coalesce with each other, and eventually the whole glass pane is covered with a sheet of water, right, as the rain continues. So it's something similar, and there are a lot more variables in what they use in VLSI processing, and sometimes you tune it. You can change the temperature of the substrate, you can increase the energy of the constituent atoms that are coming from above, you can make them move around less, you can make them move around more, whichever way we can do all these tricks. So once you have done, let us see what are the structure that you have to watch out for in a thin film. One of the key structures that you need to watch out for in thin film is the grain size. Remember that these are all coming from multiple sources of nucleation. Sometimes one nucleus orientation can overwhelm or phase of that can overwhelm the other phases and then they merge. But sometimes they retain their individuality. So you can act, and how much they retain and all that of course depends on a lot of the chemistry and the process conditions. So for thin films, generally the grain sizes would be smaller because they have just thin, they have not yet stayed for long together. But as they become bulk, the grain sizes, one will overwhelm the other and then the grain becomes dependent on the overwhelming grain phase. So the grain size actually when you are growing thin film depends on various parameters. It depends of course on film thickness. When it is thin, grain sizes clearly would be very small because they have not had a chance to interact that much with each other. Thicker leads to larger grain size. You can have higher temperature. Usually what happens is when you increase the temperature, they are able to move around much. And even within the thing, there is more vibration, so they end up rearranging a little. But that being said, there is a saturation. If you keep increasing the temperature, doesn't mean that all the grains will disappear and there will be a single grain. No. But it tends towards a single grain. It will be gradually the sizes will increase. Subsequent annealing, on the other hand, again changes the grain size, but it doesn't change as much as how much temperature could change during the deposition. During deposition, if you increase the temperature, the grain sizes could increase more than if after the deposition you annealed it. So that's why during the deposition, that's a very critical phase of the quality of the films that are forming. And then finally, deposition rate and add atom availability. Supposing you deposit a lot of them, and then those can also play a role. So critical nucleus size, sometimes the critical nucleus size can be very large. If that is the case, you will soon find all of them emerging. If the critical nucleus size is smaller, critical nucleus size means above the nuclear that critical size, nuclei is stable, chance of it dissolving is less. If that is the case, you will find that smaller critical nucleus size, you will find that the grain sizes are small. Okay, so these are things you have to study for each of the material. Another property that we have to watch out for is surface roughness. This is important because you are making a stack of films, right? Surface roughness is a higher energy state, right? But they exist in real film. In theory, if you look at it, why should the higher energy state exist? Because it's a momentary thing and it got frozen. If you had allowed time and if you had allowed the opportunity, it would have become flat. But the fact that it is not an ideal situation, you'll find that there will be some variation, and that's where in real world, although surface roughness is higher energy, they do exist in films. High deposition temperature tends to lower the roughness because there is greater chance of things to vibrate and move around and go to a lower energy state, overcoming the potential barriers. And also, they may help in developing crystal facets, because many of them have a tendency of getting a lower energy for a particular crystalline structure. So it will move towards that. At low temperature, the surface roughness increases, and it all as the thickness is increased. So as you make thicker and thicker films, and yet you are doing that at a lower temperature, the subsequent ones become more and more rougher at the surface. Another case where roughness you will find increasing is if there is oblique deposition. So that is, if there is a step or something that ends up blocking it, so you will find that that's encouraging a disorder in the surface. So shadowing effects can also end up causing a higher roughness. Epi and amorphous films can be very flat. Two extremes. Epitaxial would be totally crystalline, amorphous is totally disordered. It turns out that if done in a correct way, epitaxial of course is likely to be smooth depending on the facet of the crystal that is there, that is exposed. And on the other hand, amorphous also tends to be very flat. Amorphous silicon can be very smooth. So the measured surface area in these cases, when they are very smooth, would be equal to the geometric area. So you can actually do a surface profile with a AFM and things like that. If you can do a measurement, the area that you end up getting will be very close to the geometric area. That is, it's very smooth. The roughness is less. Another parameter in thin films is the density of film, because this will play a role in a lot of other parameters, especially electrical parameters. So density of films, how do you find it? It can be found by weighing and then measuring the thickness. Then you have the volume, because the area is there. Over the area you measured thickness, and then you know the weight, and then you can say what is the density. Sometimes you may get porous films. You may do it consciously. Porous films will be lighter. When can you do porous? For example, we just talked about low K dielectric, right? So there you may want to make it porous. So porous films will be less dense. And deposition rate, the temperature of deposition play a very important role in density of films. Sometimes after deposition, annealing also can help densify the film. That also happens because they can move around a little because of the higher energy that is given. It is similar to this analogy I had told in one of the earlier lectures. If you pour some grains in a vessel, if you pour it very fast, you may find that the volume shown is much more than what you expect. Then when you shake it, it settles down and the volume comes down, right? So the porous film formation is similar to that. Besides this, there are some thin films which are crystallographic structures that are grown, epitaxial growth. Some dielectrics tend to be amorphous typically. Okay, typically you want them to be amorphous, you don't mind them being amorphous, and that's where the properties are good. Metals, on the other hand, typically are polycrystalline. They'll form grains. So aluminum, copper, gold, silver, tungsten, all of them will have grains. Now you have to make sure the grain sizes are of appropriate size, according to which you get proper conductivity and you get proper reliability. So those are things that you should watch out when you are growing these films. So crystallographic structure is an important parameter in these films. Silicon, interestingly, can be amorphous, polycrystalline as well as crystalline depending on the deposition condition. The deposition rate has a critical role. For silicon, for example, when it is low temperature and high deposition rate, you can get amorphous, PECVD. High temperature, low rate, LPCVD, you get single crystal. High temperature, low rate would be epitaxy. And intermediate condition would be LPCVD, you will get polycrystalline. It's a slightly higher temperature than PECVD, and it's a lower pressure, so fewer atoms are coming. Instead of forming amorphous, they form a little bit of a polycrystalline structure. And of course, molecular beam epitaxy, very rarely atoms are coming. You make sure you give them time to arrange themselves, and then you get a crystalline structure for regrowth. The grain size variation, let's take some examples from literature. And of course, if you search for them, you are likely to get a lot of examples of them. I've just shown this as a representative sample, just whatever was able to get hold of. So here in this particular paper, they have shown how deposition rate changes with the growth rate. So here the values are given, and you can see that the size of the grains are increasing. Okay, and then eventually it starts coming down, saturates and then comes down. So the size of the grain depends on the deposition rate. Similarly, in the same paper, they have shown, depending on the film thickness, the size of the grain changes. And what you find is, as the grain thickness increases, you find that the grain size also increases. This is not surprising, because there is more pressure when it's a thicker thing, there's more pressure to conform. And if the critical dimension of the grains is such that it only allows larger grains, then they tend to be larger than that critical dimension. So this is just an example that I've picked up from literature. This is another thing that I saw. There's a video from Oxford Instruments where they show how the surface roughness of the film changes with thickness. So higher the thickness, you find more surface roughness is coming in this particular example, and they have shown these atomic force microscopy diagrams. Atomic force microscopy can show you what the surface profiles are and surface roughnesses. So, and that's from Oxford Instruments. As I said, silicon can have all types of crystallinity. So this is an example where silicon forms porous silicon thin film, and you can see this is how it will look from the top. There are lots of gaps in between. Porous silicon has some advantages. They oxidize really fast, and things diffuse through it also very fast. So if you want something for some special application, some regions where oxidation should be faster, make it porous silicon, and other place regular silicon. Porous silicon will have a thicker oxide. So you can have multiple oxides at the same time when you are oxidizing. So these are places where you could use them. Amorphous silicon also can be had. This is from this reference paper. Polycrystalline, as you can see, the grain sizes are larger, and this is how it looks. You can see the vertical direction, the grain sizes almost remain similar, when the horizontal direction is where the grain size is limited a little bit more. Single crystalline silicon also could be grown this way. So now that you have seen about these thin films, what are the properties that we have to watch out for, what factors affect these properties, let us take a closer look at mechanical properties of the thin films, and later we will see electrical properties of thin films. The things that I will be talking about briefly would be adhesion, how well the film is stuck to the substrate, stress in the film, stress strain curves and the properties that you get from it, and then you have also micro hardness. So adhesion of thin films. Adhesion is a must. for films. As it gets deposited, you want to make sure it sticks, the film is remaining there and is not coming off. So but that's not just when it is deposited. When the subsequent process happens, something else comes deposited on top of it, it should not end up pulling out this, because this is a weaker joint. So there is a strain that is created by the top layer and this thing comes apart. You don't want that, you want it to adhere well. One can measure adhesion by various methods, and it's fascinating how they have come up with these techniques. Some of them are very simple and commonsensical, and you could do it in your it's a sellotape method or a scotch tape method, as they say. Actually, indeed, the first one is a scotch tape method. It's a tape test. You attach a tape to the film that you have deposited. Because of the glue in the tape, it sticks to the film, and then when you pull out the tape, will the tape come out or will the film also come out? So this is a qualitative measure. You can have, if it of course comes out, you are sure that it's not very well stuck to the underneath substrate. So you have to do something, you have to do surface preparation to make it stick. You have to do some other tricks. Another is a scratch test. So here you have a hard steel, chromium steel point with which you draw a line on the film, okay, and you keep increasing the weight. So you find that at some point, as you're increasing the weight, you find at some point the gouge is becoming more and more, and after some point everything comes out. So you study that under the microscope and you know at what pressure it's actually coming out, okay, at what load it comes out. It can come out, depending on how well it is stuck, grams to hundreds of grams. Then there is another thing which is popular, is a pull test. So here what you do is, you have this thin film on the substrate. This is a substrate and this is where the thin film is deposited. You use with an epoxy, which is a very good glue, very good, very tightly bound glue. You connect it, the film, to this, and then you have an arrangement where the substrate is held this way and you pull this. As you pull this, at what point, with how much force you pull it, at what point does the glue give way, the epoxy gives way, or the film comes out from the substrate, okay. So that is what you will be studying. And of course, if you want very good adhesion, the epoxy should give way first, okay. And of course, these can be quantified to some extent depending on the amount of force you have to put. And say you are depositing under various deposition conditions, you want to see when the adhesion is best. You can easily see how much load it is, how much pull you are applying when it detaches. So adhesion energies, actually, as we have already touched upon this a little, it can vary from tens of millielectron volts to 10 electron volt. If it is less than 0.4, typically the electrons are not playing a role in the interaction between the atoms that are there close to the interface and the subsequent and the other substrate, right, of the film. So if it is physisorption based, it will be less than 400 electron volts, roughly rule of thumb, and more than 400 electron volts, it will end up becoming chemisorption. Okay, chemisorption means that it's much better the bonding is much more. Typically, when you have metals that can form an oxide, so there is a SiO2 is there, on top of it you are running a metal line. If the metal that is deposited on top of SiO2 forms oxide, it forms a very good bond with SiO2. Why? It ends up forming a metal oxide at the nano level, at the interface level, right? So titanium and aluminum, they form oxide, so they adhere very well to silicon dioxide, and that's why they have been popular for interconnects and plugs, via plugs and so on. Many times you introduce oxide forming element between the one metal and another. Metal to metal they can form an alloy, but the metal that will end up reacting to form an oxide, you will end up adhering well to the substrate. So you sometimes put chromium in between gold, because gold doesn't form oxide, and so chromium will end up forming the oxide, and chromium gold will form a small alloy, and that will be better held. it is noted that if during before deposition, if it is not cleaned properly, or during deposition or somewhere some contamination comes in, usually the adhesion is poorer. Usually that is the case. Maybe in some cases it may improve also, who knows, but usually the default is contamination means there can be some poorer adhesion. Also note, adsorbed gases can also end up causing poorer adhesion. So you have to make sure you clean the substrate well and remove any adsorption. So you may want to heat the thing initially to get rid of the gases, then bring it to the temperature at which the substrate has to be, the deposition has to take place, and then you do the deposition. Surface roughness is a mixed bag. Usually it helps. Surface roughness we don't want typically, right? Because you want a planar thing, and not just that, it may cause voids and so on. When you have further deposition, if there is very rough, you may end up having holes in the middle. You don't want all that. So surface roughness actually sometimes promotes adhesion. Why? There is more surface area. So two material, they can interact a lot more, and it's better. And also there can be mechanical interlocking at the nano level. So there are certain shapes, and they are ending up mechanically interlocked. So that also helps. So surface roughness can end up sometimes improving adhesion. Okay, but too much roughness can cause other problems, as I was mentioning, and usually you have to be careful about it. It can cause defects, which can hurt in terms of reliability and performance. The other mechanical property that you have to watch out for is stress, and in fact you have to be aware of this. All films invariably will have a stress, because it's a film, right? It's supposed to be a three-dimensional thing, you're putting in a two-dimensional thing. There is bound to be some stress that will be there. Now this stress can be classified into various categories. One is something that is because of the neighboring films, how they are putting stress on the film. Okay, sometimes it could be thermal stress. There is a thermal mismatch, and as there is within the substrate on that, and that could cause stress. And there is also intrinsic stress. Out of this, intrinsic stress is least understood. Of course, people have tried to understand, and you have theories explaining them, but so typically the stress can be broken into three orthogonal components given this way. External, whatever other film is putting on this, the thermal, which can be shown by this, the difference in the expansion coefficients of the film and the substrate, change in temperature that it undergoes when it was deposited to when it was cooled, or when it is heated up, whatever, delta T. Okay, and EF will be E sub F will be Young's modulus. Intrinsic stress is not well understood. We know that low temperature usually there is tensile stress, high temperature there is compressive stress. Higher thickness we have more stress as it is deposited. Cooling after annealing may increase stress. Okay, so you have annealed it, and then if you cool it very fast, sometimes it can increase the stress. So this is an example from Wolfentauber, which is quoted. So you can see the power of the deposition power is low, you find that the stress is tensile. Okay, so low temperature is involved here. Higher temperature that is involved, you find it is compressive. At some point it crosses zero. So that's at that temperature you will have zero stress. So you can play around with these to get what you want. And similarly, as it is deposited, you are finding that the stress keeps increasing with thickness. But on annealing, it reverses in this manner. The stress, how do you measure it? One way to do it would be interference method, capacitance method, and X-ray diffraction method. Interference method means the light, because there is a bow that is coming in the wafer, either way, it can be this way or that way. If it is tensile, the film has tensile stress, it's concave. Okay, and if it is compressive stress, it will be convex. It's going to go back to a longer length. If it is compressive, it is wanting to go back to longer length. If it is tensile, it is wanting to actually shrink. So if it is shrinking, it will bend this way. If we want to expand, it will go that way. So, and you find that sigma perpendicular is actually, sigma can be given as first order from the deformation that you have. You can say that this is the Young's modulus d divided by 6 RT, right? T is the thickness of deformation, R is the distance. Now sigma perpendicular and sigma parallel can also be given this way. Those interested, I would encourage you to read up more on this. Other thin film mechanical properties, let's go over them quickly. The stress strain curve can be evaluated, and the elastic modulus can be obtained from the slope in the linear region. This is the classic mechanical engineering you must have studied. Elongation at fracture in metal is only 1 to 2%, and they may exhibit large elastic component. Tensile strength is important, that is how much it will break or not, because if it breaks, you will have cracks in the films, right? If it is because of various stress and some intermediate step it has gone through stress, you may have cracks. Or you could have things coming up also. It will be detach itself and it will form wavy nature on top. So tensile strength value is breaking force divided by original cross section area. The tensile strength of thin films measured to be 200 times annealed bulk samples. Why? Because thin films have greater ability to adjust themselves a little. They have more room. Bulk, if an atom is there, there is atom all around, right? In the thin film, there are atoms on the sides, but less atoms on the top and the bottom. So it can adjust a little bit. So that's why you find that the tensile strength is more for thin films. And thin films usually will be more flexible. Even in the area of flexible electronics, one of the tricks to make something flexible is make it thin. Even glass can be made flexible if it is made thin. For thin films, another parameter that you need to worry about is micro hardness. Strongly correlated to the tensile strength here. Both decreases, that is tensile strength as well as micro hardness, decrease with increase in temperature. Alloying conditions can increase micro hardness. For example, copper or aluminum oxide in aluminum increases micro hardness. So if you have a film and you are putting some amount of impurities, if I may call, you may end up making it more hard. In fact, you do these tricks for various situations. Even for electromigration and all, you sometimes use these ideas. But if you have a thin film and you want to make it hard, sometimes you put a little bit of some of the things that will make it harder. So if you put aluminum, you put a little bit of copper, you'll find that it is much more hard than aluminum is a little soft material, right? You put a little bit of copper and you may end up finding that it becomes a little harder. Micro hardness knowledge is important to know bond tool pressure needed for strong wire bonding packaging. And this is where you primarily come across this. Metals, sometimes you need to do bonding and you bring wires in that, so you have to watch out for that. So in that context, you need to know how much pressure you can apply to do a proper bonding. This can be measured by pressing a hard, specially shaped point on the surface and observing indentation, and there are lots of research that has gone in here, and there are various shapes that they talk about. So when you put the pressure, how it is deforming, and with that you can make out what is the micro hardness of the material is. Now we look at some of the electrical properties. I'll talk about three simple properties. One is, of course, sheet resistance. When you talk of thin films, sheet resistance is a default that comes to mind, right? Because it's a planar process. Instead of talking resistance, you want to say how much is the resistance in the sheet. That sort of captures the two-dimensional nature of the whole thing. Then conductivity, especially for conductors, but also for semiconductors and also for insulators, because insulators you don't want them to conduct in the negative way. So this is an important parameter, especially in the area of electronics. I would think this is an important thing. And dielectric constant, as we saw, especially for making insulator dielectrics for capacitors that we end up having, or parasitic capacitance dielectrics that we are talking about. Of course, there are many other parameters both in electrical and mechanical, but I am highlighting some of the key ones. So sheet resistance. Now this is going back to your basics. This is your high school, okay? we know resistance R is equal to rho L over A. So you have a block, L is the length over which the current flows, width and thickness. So the cross section is W times T, that's through that the current is flowing. So what is the resistance that you are going to face? It will be proportional to L, inversely proportional to cross section area, and there is a constant which is resistivity. That depends on the properties of the material. So in the thin film also you have resistivity of the thin film, and of course cross section area, as I mentioned, W times T. Now when you have a sheet, you can consider to look at the resistance in terms of how many squares there are, and very often you will find these films, and especially conductors and metals, they are long lines. So instead of trying to look at a three-dimensional thing, it will be wiser to just look at how many squares there are. So to find the length of the line, I just have to count the number of squares that are in series and then add it up. Okay, and more important, this square makes you free from the dimensions in the planar space. So how does it happen? Let us see. Let us consider a square of length. Square with length is equal to width is equal to L itself. Okay. So then sheet resistance rho sub square will be what? Rho L over L times T is equal to rho over T. So you find that it becomes independent of W and L. It is independent of the parameters that are in the plane of the wafer. Only in the vertical dimension you have that playing a role. So rho sub square, so this is an important parameter. So this is known as the ohms per square or sheet resistance. This is a very important parameter in planar processing. This captures what you are doing at the various levels, not just in thin films, but also when you are, say, making a source and drain, you talk in terms of the sheet resistance of that. So how do you measure it? This is one of the popular and very convenient method. It's possible that you may have it in your lab. If not, you can try to build one or you can procure one, whichever way. So you essentially what you have is you have 4 probes which are placed quite close to each other. Through the outer probes, you can pump in a current or through one and receive the current in the other, and the inner probes you can measure the voltage that is there. So in this, actually you can model how the current is flowing. It will flow through on the surface of it, provided the space between these probes is small compared to the full substrate and dimensions that you are talking about. It's a huge substrate, so you can take it to be infinity, and then you will have this current flowing from this point to this point in all directions. So you can actually do the mathematics, and you can find that the ratio of voltage times the current that you are getting in this case 4-point probe multiplied by a correction factor, and this correction factor of course assumes that the sheet is huge and the thickness is the spacing between the needles is very small. So that is pi over natural log of 2. So that's around 4.53. So all that you need to do is in this 4-point probe, you can pump in a current of 4.53 milliamperes, for example, and then find out what is the voltage, and that would be your sheet resistance, because 4.53 will cancel here, and then of course you have to make use of the make sure you have the units correct. So it will be kilo ohms because you have used milliamperes. So this is a very popular method of finding the sheet resistance, and this is what is used in characterizing thin films. Okay, and I would encourage you to learn this simple technique because you may be able to use this in your labs when you are doing experiments. Then we talk about conductivity and dielectric constant. So let's look at conductivity first. In conductivity, what the key point to note in this thin films is the way it conducts is different. If the film is becoming very thin compared to the mean free path of the, if the current is flowing through this film, say cross section of a film, and the electron's mean free path is long enough that it ends up interacting a lot with the surface or the interface between the two ends on the sides of the film, top and the bottom of the film. So you'll find that it has to be handled a little differently. So conductivity is an important property for metals and semiconductors. Insulators should have very low conductivity. You may have what is to be noted is it will be different from bulk conductivity. You may have gold, but when you make a thin film of gold, its conductivity will not be that easy to predict. Of course, you can have a rough rule of thumb, and you can use the methods that we discussed, 4-point probe and other things, where you use rho. 1 over rho is conductivity, right? But the actual thing will be a little different because of this interaction. So and especially when the films are very porous or not dense enough as per the density of the bulk, there's no contiguity of path. So it has to take longer path, or it has to be hopping in some extreme cases. So that means that your overall physics is changing. And clearly this is a function of thickness. As you make it thicker and thicker and thicker, eventually it will go towards the bulk conductivity. So there is a simple model that has been developed by and presented in that is presented in Meisel and Glang in their handbook. So here you can talk of sigma is equal to sigma naught, which is the conductivity for the thin film, but that has to be corrected by a factor and brings down the conductivity, as you can see, 1 minus 3 times 1 minus p by 8k for k much greater than 1, and k is the ratio of the film thickness to carry a mean free path. So what it means is, if the thickness is much larger than the mean free path, you are going to get this. And on the other hand, if it is so you depending on the relative values, you get this. So you get sigma is equal to sigma naught times this, and in the other case you will get this. So this is an empirical model that they have developed, and of course trying to tune it as per the experimental data. Let's look at dielectric constant next. The dielectric thin films need low K dielectric for insulation purposes, especially back end of the line. You want to make it as low K as possible. All the parasitic capacitance are very low. You don't want them to be mutually, if there's a flipping of voltage 0 to VDD, you don't want neighboring ones to be coupled, right? So you want to make the very low dielectric constant. On the other hand, the requirement for gate oxides is become gate oxide and other capacitance. Say MIM capacitor you are making, metal insulator metal capacitor somewhere in the back end of the line. There you may want a larger dielectric in some instances. So you have to choose it accordingly, but clearly you want the conductivity to be low. So normally in the plane of we talk of conductivity not just along the plane, but also perpendicular to the plane. So not just parallel to the plane, but normal to the plane also, the conductivity should be low in these dielectrics. How do you characterize them? One of the best ways would be if you can make a parallel plate capacitor, then you can find out with the thin film as the dielectric, and you have electrodes on the top and the bottom. You'll be able to measure the capacitance and thickness. You can always measure by various means. Then with the LCR meter, you'll be able to find what the impedance is, and then you can find out what the capacitance is. So C we know is K epsilon naught A over T, where K is a dielectric constant, epsilon naught is permittivity in vacuum, and A is the capacitance, and T is the film thickness. So this is the device that you can, or the test device you can make. Insulating film you have deposited on the substrate, and if you can make the substrate conducting, or you can maybe improvise a device such that you are able to find the capacitor. So the overall capacitance is like this, and R shunt will be the leakage through this. Okay, so the Z value that you will get, you have to make sure that you are able to, the real part of that will correspond to the resistance and imaginary part to the capacitance, and you want to make the capacitance value to dominate. You don't want the leakage path to be there. And once the capacitance value is there, using the simple expression that we have studied in high school, we should be able to find out what the dielectric constant is. So let's conclude our discussion today on thin film, which is a broad overarching topic which is covering various thin film processes. Some of them we will be discussing in the subsequent lectures. So, what are the takeaways? Thin film processing is pervasive in VLSI fabrication and device processing. Higher surface to volume ratio makes thin film property different from bulk. So, that means there is a variation from what you may think from what you see in the outside world when you are making a thin film, but it also means you can sort of tune it. It gives you freedom to change stuff. Formation of thin film from atom in vapor phase to solid phase has multiple steps. We went over them in some detail. Atom formation, nucleation, nuclear growth, coalescence, channel and holes being formed, and then eventually they get filled, and then the film forms and it increases in bulk. Understanding intermediate steps help control the film property, because what happens initially sets the stage for how the overall film grows up to a significant point. So, for example, if you have the right temperature during the growth phase, you will have the right grain size. Once it is formed, annealing it will not help you later. So, it is better to be careful in the beginning. Structure of thin films is a strong function of growth conditions and parameters. That is, during the process, what are the conditions? The grain size, surface roughness, density of film, the crystallographic structure, nature. In fact, it can become completely amorphous, it can be completely crystalline by changing the conditions. Okay, so and of course you might have to have different processes for making it. You cannot use the same equipment for making all, of course, but it's about what are the conditions during the formation of the thin film. The film mechanical and electrical properties depend on the grain structures and the thickness, and they in turn of course depend on conditions of the growth. So, what are the mechanical properties that you typically have to watch out for? How you have to ensure that it adheres properly to the substrate and also to the subsequent layers that are put on top. Grain sizes, the elastic modulus, micro hardness, especially for packaging, this becomes very important. Flexible, if you want to make elastic modulus, is important. When you bend it, it should not end up changing properties too much beyond what you are acceptable to you. Electrical also similarly, sheet resistance is one of the most popular methods, and I would encourage you to learn about the sheet resistance measurement and its properties. Conductivity of film and our dielectric constant, especially in the case of capacitance. So, these are some these are some popular and primary points that I mentioned. There are clearly many more parameters that you may want to track based on what you are going to study carefully. An understanding of parameters, why is it important? Because you will be able to control your process, you will be able to have a predictable method, and also it helps design a process as per the needs of VLSI ICs and devices. Supposing you want a new type of thing, you may be able to know what to do by, if you have understood the process, what was bad you can sort of use it now to make it good, right? For example, making something porous is not necessarily always good, right? Because it will trap things, trap impurities, properties, conductivity will be poor and so on. But you may want to make sometimes porous purposely in order to get some other benefit. For example, if it's used in a sensor, maybe you may want to make it porous to increase the surface area of what it can soak in, right? So, such things you can always learn if you understand the process and have a good learning of it. Okay, so we will now continue our discussions in the next lecture about some of the thin film processes. We will start with CVD and PVD, and we will see within them examples of various processes that exist in the VLSI industry. I want to leave you with the couple of good references that are there. One is by L.I. Meisel and R. Glang, Handbook of Thin Film by McGraw-Hill, a very early book which has been very helpful for process engineers over the decades. And then there is another excellent book by Professor K.L. Chopra, Thin Film Phenomena, McGraw-Hill 1999. This also has been extremely useful since it was published. Professor K.L. Chopra, as you might know, was a faculty in our Indian academic institutions. He was at IIT Delhi, and then later he was briefly a director of IIT Kharagpur as well. But he was an expert in thin film physics. So thin film is a very important area in its own right. Okay, so with that, let's conclude our lecture for today. Thank you.